Our world is becoming increasingly complex and mysterious. Some pessimists argue that scientific progress and society itself will soon reach a dead end due to information overload. I do not believe this is a serious cause for concern. As science advances, more systems and patterns are discovered in nature. Scientific achievements lead to a decrease in the number of facts that seem disconnected. There is no need to record the fall of every apple, as thanks to Isaac Newton, we understand how gravity pulls everything, from apples to spacecraft, toward the Earth. We can understand and calculate the behavior of the simplest building blocks of our world, atoms, because the laws and forces governing them are universal. Atoms behave the same way everywhere, both on Earth and in the most distant stars. These fundamental phenomena have been studied deeply enough for engineers to develop the mechanical creations of the modern world, from radios to rockets. Our understanding of Earth has changed under the influence of great unifying ideas. For example, the theory of continental drift helps us connect a range of geological and ecological models across the planet. Charles Darwin's greatest insight, the revolution through natural selection, reveals the underlying unity of the entire system of life on Earth. Whatever individual human lives may be, our environment is neither chaotic nor anarchic. There are patterns in nature. Everything is permeated with models, from human behavior, urban growth, the spread of epidemics, to the development of technologies such as computer chips. These laws and models are great achievements of science. Discovering them required talent, and in some cases, genius. However, grasping their essence is not overly complicated. We can all appreciate music, even if we cannot compose or reproduce it. Scientific ideas can also be understood and appreciated by everyone. Science is now intruding into our lives more than ever. Many political issues, energy, health, the environment, have a scientific underpinning. How science is applied affects each of us. Important decisions should not be made solely by scientists, but should result from broad public debates. For this to happen, we all need to learn to feel the key scientific ideas. Besides their practical usefulness, they should become part of our social culture. The theory of unification, one example of which is string theory, explains how everything in the universe is interconnected. Great scientists have spent years trying to develop a theory of everything. Unlike homegrown theories that we all like to concoct, scientific theories are supported by precise data obtained from carefully planned and controlled experiments. A theory in science is the creation of a logical structure that accurately reflects both experimental observations and a deep understanding of how the world works. However, a scientific theory does not have to embody absolute truth. As long as it reflects the state of our knowledge, there is always the possibility that a new piece of evidence will emerge, disproving the theory and sending theorists back to square one. One example of this is our view of the solar system. In the 2nd century AD, the Greek philosopher Ptolemy developed a theory that placed the Earth at the center of the solar system. This was a logical explanation based on the primitive astronomical observations of the time. However, in the early 17th century, the Italian astronomer Galileo Galilei began observing the heavens using a newly invented telescope, which made observations of the solar system much more accurate than those made with the naked eye. In his observations, Galileo discovered details that aligned with the new theory proposed by the Polish astronomer Nicholas Copernicus. put forth 100 years earlier. Copernicus's theory depicted a familiar picture. The Sun, not the Earth, is at the center of the solar system. Since then, many observations, including data from space exploration, have confirmed the heliocentric model of the solar system. Other failed theories include the flat Earth theory, the phlogiston theory, an early attempt to explain the origin of fire, and the so-called theory of intelligent design. Our theoretical understanding of nearly all branches of modern science has evolved as old, outdated theories have been replaced by new and improved ones. Today, the core of scientific knowledge permeates all fields, from the origin of the universe to the workings of the human mind. The principle of least action states that actions are performed in a way that requires the least effort. For instance, a beam of light will travel in a straight line, as this is the shortest path between 2 points. If you throw a ball, it will head toward the center of the Earth. It is not precisely known who first proposed the principle of least action, but if you think about it, your everyday experience will likely lead you to this idea. However, in the 18th century, this question was a matter of dispute. Some of the greatest mathematicians, such as Leonhard Euler, Pierre de Fermat, Gottfried Leibniz, and Voltaire, debated who first put forth this idea. At that time, it was important to generate such ideas, as they led to the creation of equations describing the motion of bodies under the influence of forces. They also led to the concepts of potential and kinetic energy. The principle of least action, unlike other theories, is merely common sense. Movement in nature always chooses the simplest and shortest path. When Isaac Newton sat down and pondered how objects move, he developed 3 laws that have become so familiar to us that they seem self-evident. First, he stated that a body has inertia, meaning it can resist changes in its motion. Inertia means that an object remains stationary until you give it a push. Similarly, moving objects continue to move unless something stops them or accelerates them. Second, the mass of an object determines what effect a given force will have on its motion or lack thereof. The third law, the most famous, states that for every action, there is an equal and opposite reaction. If I push you, you will feel an equal push in response. This principle is how rocket ships and jet engines operate. When exhaust gas is expelled from a nozzle, the engines are propelled forward. That is why you should be careful when stepping out of a boat. As you move forward, you will inevitably push the boat backward. If you do not take this into account, you risk ending up in the water. The laws of motion are all that is needed to describe how bodies move in everyday life. Newton's ideas made future journeys to the moon possible. It took 300 years to invent what was necessary for that. The law of universal gravitation is a description of one of the fundamental forces in nature and is one of the greatest achievements of science. Isaac Newton formulated this law in 1687 as part of his brilliant 3-volume work on mathematics. The law of universal gravitation states that everything that has mass, that is, everything made of ordinary matter, exerts a mutual attraction. This attraction depends on the masses of the 2 objects, the distance between them, and a constant known as the gravitational constant. One of the central ideas of this theory is that gravitational forces follow the inverse square law. This means that the attraction between 2 bodies decreases with a value equal to the square of the distance between them. Newton's formulation of this law was so accurate that it immediately explained the motion of planets. It also made it possible to launch rockets into space. After Einstein proposed the theory of relativity and explained some anomalies in planetary orbits with it, it became clear that Newton's law was not the final word on gravity. However, it is almost universally accurate when applied to the gravitational attraction we encounter in everyday life. Large or small, everything falls to Earth with the same likelihood. Imagine what you would see if you were sitting on a beam of light. This question was posed by Albert Einstein when he was still a boy. The answer he found, the theory of relativity, destroyed the orderly universe described by Sir Isaac Newton. 2.5 centuries later, nearly 100 years after Einstein, modern physicists are still trying to understand what his theory truly means. Albert Einstein was born in southern Germany in 1879. His father, Hermann, was an unsuccessful entrepreneur. When the family's fortunes declined to the point of desperation in the 1800s, Albert was left alone in Germany to pursue his education while his parents went to work in Italy. During this time, Albert had already begun conducting his own scientific research and dropped out of high school at the age of 16. Despite his lack of formal education, he secured a place at the Polytechnic Institute in Zurich in 1906. Einstein continued to study extensively at home, but his attendance at college was poor. After graduating, his bad reputation hindered him from pursuing a teaching career. He began working at a patent office in Bern and married Mileva in 1903. His unremarkable job left him with plenty of free time to ponder physics. The year 1905 became a year of wonders in Einstein's life. He published 4 papers, one of which, on the connection between light and electricity, earned him the Nobel Prize. Another paper became the starting point for the theory of relativity. 10 years later, Einstein published the general theory of relativity. This theory unified his ideas about energy, mass, and gravity into a single concept called SpaceTime. His life was shaken by World War and personal troubles, but Einstein continued to work. His main goal was to connect relativity with theories about atoms, creating a unified theory of everything. This work remained unfinished after Einstein's death in 1955, and still remains so. Step into the sea, expose your body to the waves, and you will feel how much energy they contain. Surprisingly, they carry energy in completely different ways. Some waves, such as ocean and sound waves, physically move particles of water or air or any other medium through which they pass. These waves come in 2 types. A sound wave is longitudinal if it creates vibrations that move air parallel to the direction of the wave's motion. Transverse waves, such as electromagnetic waves, oscillate in a direction perpendicular to their motion. Polarizers and sunglasses are effective because they block transverse oscillations moving in a specific direction, such as up and down. Any light waves oscillating in a different direction, such as side to side, pass through unchanged. If light were a longitudinal wave, polarizers and lenses would be utterly useless. Much of wave theory was developed in the 19th century when pioneers like Thomas Young demonstrated how to manipulate waves. Waves are reflected by certain materials, refracted when passing through the boundary between 2 media, or diffracted when passing through a narrow opening. Waves are everywhere, in the ocean, in the air, and even in the vacuum of space. Wherever they are, All waves have a wavelength, the distance from the beginning of one phase to the beginning of another. If a wave moves at a speed of 1 wavelength per second, it has a frequency of 1 hertz. An ocean wave may have a frequency of 0.2 of a hertz, while a light wave has a frequency of about 500 trillion hertz. If you want to understand how heat moves, you should master thermodynamics. This theory is governed by 3 laws. The first states that whatever happens, the total energy in the universe remains constant. In other words, you cannot create or destroy energy. You can only convert one form of energy into another. The second law asserts that the entropy of a closed system always increases. Entropy is the part of the internal energy of a closed system that cannot be used in any way. Thus, as a clock spring unwinds, it has less and less force to keep the clock running, and entropy increases as the potential energy of the spring is slowly transferred to the hands as kinetic energy, with some energy lost as heat due to friction in the mechanism. The third law states that as the temperature in a system approaches absolute zero, the lowest possible temperature, minus 273.15 degrees Celsius, all natural processes cease, and entropy reaches its minimum. Consequently, reaching absolute zero is impossible, as no processes can take you there. According to thermodynamic theory, a refrigerator does not add cold to your food. It removes heat from it. It does this by compressing a liquid in tubes on the back of the appliance. An aerosol becomes cold when you use it. A refrigerator works similarly. An expanding liquid turns into a cooling gas, and then the compressor turns the gas back into a warm liquid. Electromagnetism is an incredibly powerful idea. Without it, our lives would be unrecognizable. It describes what happens when electric charges, motion, and magnetic fields are combined. Move a metal conductor within a magnetic field, and an electric charge will rush into that conductor. This is how we generate electricity. Conversely, send an electric current through a conductor, and the movement of electric charges will create a magnetic field. This is how we create electromagnets, which power most doorbells and particle accelerators. The third option is to pass an electric current through a wire located in a magnetic field. The wire will start to move. This idea led to the creation of electric motors in your kitchen blender and electric drills. The theory belongs to the Scotsman James Clerk Maxwell, who was the first to write down the equations describing the complex interactions of electric and magnetic fields. It turned out that the equation required an unexpected component, the speed of light. This discovery led to the understanding that light and radiant energy can be represented as moving oscillations in electromagnetic fields. These moving fields became known as radiation. Remarkably, a stream of invisible particles and the influence of an invisible force field can energize everything, from a toy car to a super powerful computer. An electromagnet is a magnet that has received energy from an electric current, allowing it to be turned on and off. Such magnets are used in electric motors. Einstein's theory of relativity is the most precise description of how matter, energy, space, and time interact. There are actually 2 theories, special relativity and general relativity. Special relativity came first. It stated that nothing can move faster than the speed of light. It also showed that the passage of time is different for people traveling at different speeds. According to this theory, if you separate twins and send one on a journey through space at a speed close to the speed of light, then when they meet again, their ages will differ significantly. Special relativity also gave rise to the famous equation E equals mc squared, which describes how matter can be converted into energy and vice versa. This equation formed the basis for the atomic bomb and nuclear energy. The later theory, general relativity, changed the understanding of gravity proposed by Isaac Newton. It describes time as a dimension, just like the three dimensions of space, and unifies them all into something called SpaceTime. Everything is relative. We often say these words, but we do not fully understand how true they are. Even time, mass, and space are interconnected. According to the theory of relativity, the faster you move through space, the slower you move through time. If you reach the speed of light, time will come to a complete stop. Atomism was originally proposed in the 5th century BC by the Greek philosopher Democritus, who believed that everything in the world consists fundamentally of combinations of tiny, solid, and invisible particles. He called these particles atoms and suggested that they come in various shapes and sizes, but all consist of the same fundamental material. Modern scientific theories of matter assert that the vast array of substances we observe in the universe consists of combinations of various chemical elements. These elements are indeed made up of trillions of identical particles or atoms. The internal structure of an atom is characteristic of each element. Thus, a hydrogen atom has a different structure than a gold atom. Modern atomic theory began in the early 19th century with the work of English chemist John Dalton. However, it was only in 1905 that Einstein mathematically proved the existence of atoms. A few years later, Ernest Rutherford became the first to look inside atoms in an experiment where he bombarded a thin sheet of gold with alpha particles. He discovered that each atom consists of a tiny positively charged nucleus surrounded by empty space, in which even smaller negatively charged electrons orbit around the nucleus. Everything you have ever seen, can see, and will see in the future is made up of a multitude of atoms, even you yourself. This incomprehensible yet incredibly powerful theoretical representation of the subatomic world, where everyday concepts of forces and motion no longer apply in the usual way, requires a new kind of mechanics based on quantum rules. This idea was first developed in the early 20th century by German physicist Max Planck, who proposed that energy comes in tiny fragments called quanta. In the 1920s, Albert Einstein, Niels Bohr, Paul Dirac, and Werner Heisenberg continued work on this theory. However, despite its enormous success, quantum mechanics remains shrouded in mystery, as, unlike other scientific theories, no one knows exactly how and why it works. It makes some predictions about the microscopic world, and they completely contradict our common sense. For example, it explains how an atom can exist in more than one place simultaneously until we check where it is located. It also claims that an electron can spin both clockwise and counterclockwise at the same time until we measure it. Quantum mechanics asserts that the same subatomic particle can exist simultaneously in a whole range of different states. The Heisenberg uncertainty principle is a theory about how quantum objects, such as atoms and smaller particles within atoms, behave. The principle was developed in 1920 by Werner Heisenberg and named in his honor. According to this principle, we can never know exactly where an electron is located, although we can know exactly how fast it is moving. Both qualities, its speed or position, can essentially be measured infinitely accurately if we sacrifice the value of the other quality. It is not due to a lack of understanding of how nature works, nor is it because of the tiny size of the electron. It is simply that electrons are such by nature. This has nothing to do with us. The electron itself does not have a precisely defined position and speed. The best we can do is determine the region where the given electron is most likely to be moving. The uncertainty principle also touches on concepts such as energy and time. We can measure the exact energy of a particle as long as we do not question at what moment in time it possesses that energy. Conversely, if we precisely define the time of measurement, we must abandon all hope of knowing how much energy it possesses. According to the uncertainty principle, measuring subatomic particles allows you to obtain only a limited amount of information. In the mid-1930s, Austrian physicist Erwin Schrödinger proposed a thought experiment to illustrate how bizarre quantum mechanics is. He suggested taking a box and placing a cat, a small amount of deadly poison, and a source of radioactive decay inside it. According to quantum mechanics, we cannot say until we check whether the radioactive atom has decayed within a given time frame, so we must describe it as both decayed and not decayed. Only after checking do we force it to be either one or the other. Inside Schrödinger's box, the experiment is set up so that any decayed atom will release a particle that triggers the release of the poison, killing the cat. Since the cat, according to Schrödinger, is also made of atoms, albeit trillions of them, it is also presumed to be subject to the laws of quantum mechanics. So, until we open the box and look inside, we must describe the cat as simultaneously both dead and alive. Only when we open the box do we determine everything inside it as being in one of those states. Schrödinger used his thought experiment, the cat in the box, in a debate with Albert Einstein, but it also helps us describe how quantum physics works. Richard Feynman and his many collaborators reshaped our understanding of quantum physics. It is a world of incredibly tiny particles that make up the fabric of the universe. Like all brilliant scientists, Feynman was an independent free thinker. He is known not only for his insights, for which he was awarded the Nobel Prize, but also for his playful antics with a can. Richard Feynman was born in New York City in 1918. He was a physicist who primarily understood them as waves. While working at Princeton University, Feynman was involved in early research on atomic weapons. In 1943, he went to the Los Alamos National Laboratory in New Mexico as the youngest member of the Manhattan Project. There, he helped calculate the explosive power of atomic bombs and set up a primitive computer system to analyze the vast amounts of data generated by this project. In 1950, Feynman became a professor at the California Institute of Technology. There, he, along with Murray Gell-Mann, sought to describe the weak force within atoms. This work explained what happens when radioactive atoms decay or break apart. Feynman's lectures at the California Institute of Technology inspired a new generation of particle physics specialists, and his books on various topics captivated the general public. Feynman continued to work at the California Institute of Technology until his death in 1988. A field in physics refers to a region of space where a physical influence is exerted on bodies. Examples of this include gravitational and magnetic fields. Therefore, Field theory describes how these fields behave and how bodies interact with the fields they are in. At the end of the 1920s, one of the founders of quantum mechanics, Paul Dirac, published several papers showing that quantum theory could be unified with James Clerk Maxwell's theory of the electromagnetic field, as well as with Einstein's theory of relativity. He created the first quantum field theory, which described the interactions of electrons and photons, the particles of light. In 1949, several physicists, including the great Richard Feynman, developed quantum electrodynamics. Later, this theory was used to unify the electromagnetic force with another of the four fundamental forces of nature, the weak interaction. This development became known as the theory of electroweak interactions. A separate quantum field theory, known as quantum chromodynamics, was created to describe strong interactions, the last of the four forces of nature, gravity. To this day, attempts to become quantum in nature have been thwarted. Quantum field theory applies the strange laws of quantum physics not only to solid particles, but also to fields, describing the fundamental forces of nature. This theory is not simple. When two quantum objects, such as electrons or photons, come into contact, their quantum states, the mathematical information describing their qualities, combine or intertwine. Their fates then remain intertwined, no matter how far they advance in the future. While it is easy to believe that two objects with a shared past during their interaction will somehow influence each other's qualities, the result of this interaction will be noticeable later when we check these particles. However, the theory of entanglement can be much stranger. In the quantum world, bodies can exhibit two or more incompatible qualities simultaneously. For instance, spinning in opposite directions at the same time. This is called superposition. For example, if one photon is entangled with another, it can infect it with its superposition, causing both to be in superposition. However, by observing one of them, we force the photon to decide which path it will take. But since it is entangled with its partner, we also force the other photon to make the same choice. This will happen instantaneously, even if the two photons are now separated by millions of miles. Subatomic particles are connected to each other, even if separated by vast distances. Will we ever be able to untangle quantum entanglement? Someday, quantum entanglement may allow objects and people to teleport across vast distances. This is an attempt to describe in a single theory the workings of all four fundamental forces of nature and the relationships among all elementary particles in physics. Forces can be characterized by fields that transmit interactions between particles. They are known as field theories. For instance, in 1915, Albert Einstein developed the general theory of relativity, the field theory of gravity. At subatomic distances, fields are characterized by quantum field theories that apply quantum mechanics ideas to the fundamental fields associated with the other three forces, the electromagnetic force and the strong and weak interactions. Currently, scientists aim to understand whether quantum chromodynamics, the theory of strong interactions, can be unified with the electroweak interaction theory, which describes the electromagnetic force and weak interactions. The result would be the so-called grand unification theory. However, a successful grand unification theory still will not include gravity. The problem is that physicists still do not know how to formulate a real quantum field theory of gravity. One possible candidate for such a theory of everything is the so-called string theory, but we are still far from understanding whether it is correct. In the universe, everything is interconnected. This is easy to say, but understanding how to prove it is very difficult. All the stars we observe in the sky are part of a system called the Milky Way galaxy. The Milky Way consists of hundreds of billions of stars, and hundreds of billions of galaxies are scattered throughout the cosmos. Most are grouped together, held by gravitational force. Clusters of galaxies resemble a vast swarm of bees moving as a single entity. Studying the motion of groups of galaxies shows that over time they are moving away from each other. The best evidence for this is the redshift of light from distant galaxies. Redshift, literally the reddening of galactic light, shows that each cluster is moving away from other clusters and the center. There is no center to this expansion. This is explained by the general theory of relativity as a result of the expansion of space between the groups. Thus, long ago, all galaxies, stars, and matter in the observable universe were gathered in one place, in a hot energy clump the size of a grapefruit, known as the Big Bang. By measuring the speed at which galaxies are currently moving away from each other, astronomers estimate that the Big Bang occurred 13.7 billion years ago. Imagine a grapefruit weighing as much as the entire universe, heated to billions of degrees. Since the amount of light emitted by a star depends on its mass, astronomers can weigh galaxies by measuring the brightness of their stars. Since gravitational force affects the motion of objects, astronomers can weigh the universe by studying the motion of galaxies and the rate of expansion of the universe. All the bright stars in all galaxies account for less than 1% of the mass needed to explain how galaxies move and how the universe expands. The study of how atoms and particles, which make up you and everything around you, formed during the Big Bang, shows that there may be approximately 4 times more dark atomic matter in the gas and dust clouds between stars. This is referred to as baryonic matter, as it consists of baryons found in the atoms of large particles. It is currently believed that baryonic matter accounts for about 4% of the mass of the universe. The motion of galaxies indicates that there is 4 to 5 times more non-baryonic dark matter, composed of smaller subatomic particles. However, around 74% of the mass needed to calculate the expansion of the universe has yet to be found. The light from stars in the universe is insufficient to determine its weight. Most of the matter in the universe is too dark to be observed from Earth, and vast regions appear completely invisible. The Big Bang theory includes an event known as cosmic inflation, before the universe expanded into an incredibly hot fireball that has since cooled and transformed into galaxies and stars. It was concentrated in a single point. Quantum uncertainty allows tiny energy clumps to arise from nothing. However, if such a bubble contains a form of energy known as a scalar field, it can act like anti-gravity, causing the bubble to expand at maximum speed until it reaches a volume of about 10 centimeters in diameter, roughly the size of a grapefruit, before the field releases its energy in the form of heat, and the anti-gravity effect ceases. At the end of the process, the inflationary model of the universe represents a fiery clump of energy, a grapefruit-sized sphere that continues to expand, but more calmly as a result of the inflation. This Big Bang theory suggests that a specific pattern of waves was imprinted on the space-time of the grapefruit stage. These fluctuations provided the oscillations that allowed galaxies and clusters of galaxies to grow through gravitational merging as the universe continued to expand. Nothing can move faster than light. Only space-time itself can do so. During the period of cosmic inflation, the expansion of the universe broke the cosmic speed record. The universe we live in is perfectly suited for our existence. If gravitational forces were slightly stronger, stars would be smaller, using their nuclear fuel faster and burning out before complex life forms like us could emerge and evolve around them. According to the Anthropic Principle, we can use the facts of our existence to predict the values of certain qualities of the universe, such as the strength of gravity. It is known that in the 1950s, astronomer Fred Hoyle used this argument to predict specific qualities of carbon atom nuclei, as our form of life depends on carbon, and without these qualities, carbon could not be created within stars, and we would not exist. Hoyle's later assumptions were confirmed by experiments. Then the question remains, why is the universe, like the porridge of Goldilocks in the tale Goldilocks and the Three Bears, just right? Some believe this means that the universe was designed for us. Others think there are many universes, and life exists only in those that resemble our own. Earth's place in the universe is akin to the porridge of Goldilocks. It is not too hot and not too cold. It is just right. Is this mere coincidence? What shape does the universe take? Topology is the science of shapes and how one shape can transform into another. Do not tear. It is thought to be a torus. This is a person who cannot distinguish a donut from a coffee cup. If the donut were made of rubber, you could stretch it and shape it into a cup. The inner ring becomes the handle of the cup, while the rest of the donut transforms into the body of the cup. Most astronomers believe that the universe is infinite. However, if it were finite, it could take the shape of a very large donut. If that were the case, looking one way around the donut ring, you would see the same galaxies as if you were looking the other way around the ring. In a more complex topology, imagine a cube where opposite faces are connected. If you traveled in a spaceship through the roof, you would return to the cube through the floor. Even if the universe is finite, observations suggest that its topology is not so simple. Research into the radiation left over from the Big Bang suggests that the universe may take the form of a 5-dimensional, 12-dimensional space, very similar to the 3-dimensional arrangement of fragments on a soccer ball. For topologists, coffee and donuts are inseparable. For them, a donut and a coffee cup have the same shape, differing only in the lengths and angles of their sides. It is believed that our universe arose when cosmic inflation occurred in a tiny part of empty space. Even today, dark energy causes the universe to expand ever faster and distributes matter within it even more thinly. Ultimately, only empty space will remain. Then inflation could create even more worlds in this empty space. Consequently, our world is one of many that arose in a previous phase of the process called eternal inflation, which has no beginning or end. This could lead to an infinite number of bubble universes. Therefore, there is no reason to expect that the laws of physics will be the same in every world. Some universes will be suitable for life, while others will not. This explains the puzzles of anthropic cosmology. It also means that there will be worlds in which any conceivable possibility actually occurs. A world where the South won the American Civil War, and a world where dinosaurs never went extinct. Perhaps in other worlds, there are other Earths similar to ours. Dark energy accelerates the expansion of the universe. If this continues, and there are no reasons to believe it will not, the expansion will increasingly accelerate over time. Initially, this will not directly affect matter. Within galaxies, stars will continue to be born, live their lives, and die. However, as the material from which stars are made is consumed, galaxies will weaken, and more matter will accumulate within various forms of dead stars, white dwarfs, neutron stars, and black holes. However, while this is happening, clusters of galaxies will drift apart faster and faster, disappearing from view. Our own Milky Way galaxy is part of a small group called the local group. In a couple of 100 billion years, a period approximately 10 times the current age of the universe, nothing visible will remain beyond the cosmic archipelago. Eventually, the cosmos will expand so rapidly that it will overcome the force of gravity and other forces, tearing material objects apart. The result will be a rapidly expanding cosmos in which matter is distributed so thinly that it will essentially become empty. These are ideal conditions for the birth of one or more new worlds. Due to inflation, it will take several more years, to be precise, 1 more 11 pores. But ultimately, the forces that created the universe will tear it apart. The erotic theory owes its name to the Greek word meaning born in fire. Another name is the Phoenix universe. According to this idea, our universe is one of two three-dimensional worlds separated by a tiny space, the mini diameter of an atom in the fifth dimension. In reality, this is the fourth dimension of the cosmos, but the term fourth dimension has already been claimed by time. Every point in our cosmos is adjacent to a point in another world. Currently, the two worlds are slowly moving away from each other. Additionally, each world is expanding, igniting its contents. Eventually, they will turn into empty, expanding space. By then, the forces and the source will once again bring both worlds together along the fifth dimension. The energy released during the collision of the two worlds will transform into matter, creating a new Big Bang. And due to quantum effects, different parts of the two worlds will touch each other at slightly different times, creating fluctuations that are the seeds from which galaxies grow. Then the worlds will drift apart, and the entire process will repeat. It happens continuously. This is the main alternative explanation for the Big Bang, and it does not require the initial phase of inflation. Give me your five-dimensional space-time, and I will give you a parodic universe in which we oscillate back and forth with an invisible partner universe involved in a constant sequence of Big Bangs. Planets formed from a cloud of particles as dispersed as smoke orbit the Sun in a disk shape, like Saturn's rings. The particles begin to stick together as they all move along the same path around the Sun and frequently collide with one another. Eventually, they become large enough and start to attract each other. Gravitational forces continue to grow, with larger fragments absorbing smaller ones and becoming early planets. These larger fragments collide with one another, break apart, and recombine many times until they settle down and become the planets we see today. No one knows for sure why 4 small dense planets are located near the Sun, while 4 large gas giants are farther away. It is likely that the planets close to the Sun had difficulty retaining gases that were blown away by solar radiation. In contrast, the gas giants could accumulate icy particles beyond the zero-temperature boundary, meaning at a distance from the Sun, where not only glacial water melts, but also other frozen substances such as methane and ammonia. From tiny dust particles, giant planets grow. The planet Earth, the Sun, and the other planets of the solar system formed from a vast cloud of dust and gas that slowly collapsed under the influence of their own gravitational forces. Our planet is never stationary, and even continents are constantly drifting, moving in a slow dance across the Earth's surface at about the same speed that fingernails grow. Throughout Earth's history, there have been times when this dance gathers all the continents together, creating a giant supercontinent until they once again go their separate ways. This happened about 1.3 billion years ago when Rodinia formed, and it was repeated 250 million years ago with Pangaea. The idea of continental drift itself is quite old. In 1596, noticing the compatibility of the coastlines of Africa and South America, Belgian cartographer Abraham Ortelius suggested that America was forcibly pushed away from Europe and Africa by earthquakes and floods. However, it took another 300 years before German scientist Alfred Wegener proposed the theory that continents are constantly moving. However, without a mechanism explaining how this is possible, this idea was not truly accepted until the early 1960s. By that time, new geophysical facts showed that the movement of continents was accompanied by the expansion of the ocean floor and was driven by currents in the partially molten layer beneath the solid crust and the very upper part of the mantle. The ground beneath our feet is not entirely solid, and it is constantly moving. As you might have guessed, the Snowball Earth theory suggests that in ancient times, Earth was covered by glaciers, making it resemble a giant snowball. Proponents of this theory, including American biologist Joseph Kirschvink, who coined the term, believe that during the Cryogenian period, approximately 850 to 630 million years ago, a weak sun and low concentrations of greenhouse gases in the atmosphere led to a dramatic drop in temperature on the planet. A key point of the theory is the extraordinarily low concentration of greenhouse gases, and there are many possible scenarios for its occurrence. One scenario is that the joining of continents near the equator provided ideal conditions for extensive tropical erosion, where carbon dioxide in the atmosphere reacted with rocks, creating solid minerals. As a result, the concentration of gas in the atmosphere sharply decreased. Once the planet was enveloped in ice, it became difficult to warm up to the temperature needed to melt the ice, as the white surface of the planet reflected much of the solar radiation back into space. The only possibility was an increase in heat from the sun, or a rise in the level of carbon dioxide in the atmosphere, possibly due to gases released during volcanic eruptions. The white surface of frozen Earth reflected solar heat back into space, maintaining a cold temperature. James Lovelock is one of the few independent scientists of modern times. He did not work in a university or government laboratory for 40 years. Direct and radical, Lovelock is both a scientist and an inventor, as well as a visionary. His most well-known theories are the Gaia hypotheses, descriptions of how Earth self-regulates. They have not been fully accepted by the scientific community, which has raised concerns about the methods Lovelock used to test his ideas, although this theory is quite compelling. It is uncertain whether the Gaia hypothesis will ever become a useful tool for other scientists. James Lovelock was born in the town of Notting Hill, north of London, in 1919. He studied chemistry in Manchester until he transitioned to the National Institute for Medical Research in 1941. Much of his early work at this institute was related to military developments. He invented an underwater monitor for measuring blood pressure and a device for measuring the speed of sound. After 20 years at the institute, Lovelock moved to NASA. There, his knowledge was used to create detectors that could analyze the composition of rocks and the atmosphere of the Moon or another distant planet. Many of the space research rockets equipped with Lovelock's devices were tested for evidence of life. Lovelock realized that the most obvious evidence of life on another planet is its dynamic atmosphere. With a constantly changing atmospheric composition, the atmosphere of a dead planet remains unchanged. Reflecting on how life has altered Earth's atmosphere led Lovelock to develop the Gaia theory. Lovelock left NASA in 1964, returned to the UK, and became an independent scientist and inventor. In 1979, he published his first book, simply titled Gaia. It was soon embraced by the environmental specialist community, but rejected by many scientists who claimed it was based on New Age philosophy rather than objective scientific research. However, many believe that the Gaia theory has proven useful, launching a long series of studies and debates. In 2004, Lovelock reaffirmed his reputation as a free thinker when he declared that nuclear energy is the best way to regulate climate change. This time, the criticism came from environmentalists. Global warming is a rather innocuous term for the continuous and inevitable heating of our planet. Earth is an incredibly dynamic planet whose climate has experienced sharp fluctuations in temperature over its 4.6 billion year history. We live in a mild world of an ice age between the last ice age, which ended about 10,000 years ago, and a future ice age. Typically, between ice ages, the level of carbon dioxide, the primary greenhouse gas that retains cosmic chill, remains unchanged, stopping solar heat at about 280 millionths. However, due to pollution from a 200-year period of industrialization, it has now reached 385 millionths and continues to rise. Although there are skeptics who refuse to acknowledge the human factor in global warming, the link between carbon dioxide emissions and the heating of the planet is not new. In the 1890s, Swedish chemist Svante Arrhenius calculated that doubling the concentration of carbon dioxide in the atmosphere would lead to a rise in temperature across the planet by 4 degrees Celsius. While our planet has warmed by 0.74 degrees Celsius, Arrhenius's prediction is likely to come true around the year 2000, provoking chaos and environmental degradation. Some enjoy the warmth, but global warming will make the climate not warmer and sunnier, but harsher. Prepare for strong winds and heavy precipitation. It is believed that the temperature on Earth depends on the amount of greenhouse gas emitted by industrial enterprises. The catastrophe theory is based on an idea beloved by Hollywood blockbuster creators. Earth periodically experiences unpredictable short-term catastrophes with global consequences. This worldview is born from the thought that catastrophes are acts of God sent to punish people. Such notions are borrowed from biblical tales of Judgment Day and disasters like the Great Flood. In the 18th and 19th centuries, the catastrophe theory reached its peak as a scientific theory, when naturalist philosophers debated the history of the Earth, marked by catastrophic events occurring over a span of just a few thousand years. Probably the most famous proponent of the catastrophe theory was French paleontologist Georges Cuvier, who linked catastrophes to mass extinctions. In the mid-19th century, the catastrophe theory was supplanted in scientific circles by uniformitarianism, a concept introduced by Scottish polymath James Hutton and popularized by English geologist Charles Lyell. Unlike the catastrophe theory, this concept acknowledges that the history of the Earth is marked by successive, gradually increasing changes, involving the same physical processes that we observe today in the world around us. About 65 million years ago, most giant reptiles suddenly went extinct. The list of causes for this catastrophe ranges from the impact of a large meteorite and volcanic eruptions to the disappearance of ferns that served as their food. The Gaia hypothesis was formulated in the 1960s by English scientist James Lovelock, who described Earth as a living, self-regulating organism. While this does not mean that our world is actually alive, it consists of complex, interrelated interactions between life and the physical environment, the atmosphere, oceans, polar ice, and the rocks beneath our feet. According to the Gaia hypothesis, these interconnections work harmoniously to maintain Earth in a state necessary for sustaining life. This balanced state, sometimes referred to as homeostasis, is characteristic of living organisms themselves, which can manage their internal processes to maintain the status quo. In support of his ideas, Lovelock pointed to the extraordinary stability of Earth's surface temperature over long periods, despite the increasing solar radiation. He also noted the consistency of ocean salinity and atmospheric composition, despite the presence of many factors that could and should have disrupted these parameters. Lovelock's Gaia hypothesis has faced sharp criticism, particularly from biologists. However, the idea that life plays a key role in maintaining the habitability of our world continues to attract interest and support from prominent scientists. Lovelock's model of the world is a simple model of how life on Earth has responded to changing conditions on the planet's surface. Earth may be a rare example of a home for intelligent life. Over 4 billion years of evolution were required for our civilization to emerge on a calm, stable planet orbiting a calm, stable star. The Sun is an unusually stable star, and it has been a reliable source of warmth throughout the evolution of life on Earth. Jupiter, our giant neighbor, protects Earth from comet bombardments by sucking in these icy bodies before they can reach us. Yet even under such conditions, several of Earth's largest catastrophes, including the extinction of the dinosaurs, are linked to comet impacts. Without Jupiter, such impacts would have been so frequent that intelligent life would not have had the time to evolve. Earth's enormous moon is also extremely important. It stabilizes Earth and prevents it from wobbling side to side like a spinning top. The periodic forces exerted by the moon within Earth maintain its heat and support the magnetic fields that protect us from harmful cosmic rays. The same forces drive oceanic tides, which played a significant role in the emergence of life on land. Life on Earth became probable due to a multitude of fortunate events. For instance, our giant moon helps us in many ways. 100 years ago, Swedish scientist Svante Arrhenius proposed that life in the form of spores could survive in space and spread from one planetary system to another. According to Arrhenius, randomly moving spores escape from a planet's atmosphere and disperse throughout interstellar space due to the weak but constant pressure of radiation emitted by starlight. The modern version of the Panspermia idea originates from observations of prebiotic materials in interstellar clouds. Evidently, some substances from this raw material, such as amino acids, fell onto young Earth and initiated the process of life there. Some researchers, particularly Fred Hoyle and Chandra Vikram Singh, argued that not only complex organic substances, but even fully formed living organisms, such as bacteria, could develop in space on the surfaces of dust grains and then reach Earth via a colliding comet. There is also the possibility of ballistic panspermia, where comets from one planet were ejected into space and traveled to another planet. The discovery of meteorites on Earth from the surface of Mars suggests that we may have originated from Martian bacteria. Did life on Earth originate from space? Did Earth spores sow life on other planets? A person suffering from angina or allergies is infected with bacteria that spread through these body parts. The illness is treated with antibiotics. A small dose of the medication prevents the reproduction of bacteria and infections and nearly disappears. However, after a few days, it may return as antibiotic-resistant bacteria take the place of the ones that were destroyed. The transition from a drug-susceptible population of bacteria to a population of resistant ones is the most vivid example of natural selection. The action of drug resistance is passed on to the next generation of bacteria, and eventually, this trait becomes inherent in all members of that population. This process occurs in all organisms capable of passing on certain traits to their offspring through reproduction. However, errors in the process ensure that each individual offspring is unique, albeit in minor details. Evolutionary changes usually take much longer, but a similar process that alters a group of bacteria explains the evolution of life on Earth over 3.5 million years. Natural selection ensures that life adapts to various conditions in its attempts to survive. The theory of natural selection asserts that species evolve to overcome challenges in their habitats. The theory of evolution through natural selection is a powerful blow to religion. It explains the emergence of complex organisms that were previously thought to have been created by a creator. Apparently, the traits of living beings benefit their possessors. When a cat eats a mouse, it employs sensory systems, eyes, whiskers, and so on, along with the muscles of its paws and digestive system, all to survive another day. These traits emerged as a result of natural selection. Thus, natural selection leads to the emergence of qualities that assist living beings. However, these same organisms sometimes exhibit altruism. One individual sacrifices itself to save others. Altruism contradicts natural selection, and it was previously thought that self-sacrificial behavior benefited species. However, no mechanisms capable of explaining natural selection at the level of all organisms have been discovered. Altruistic behavior makes more sense when considering the benefits it brings to the genome of close relatives. For example, two sisters share at least a few identical genes. One sister may sacrifice herself to ensure the survival of the other. The deceased sister cannot pass on her genes, but the genes she shared with her sister will survive her death, benefiting the selfish genes that die protecting their sister. The selfish gene theory emerged in the 1960s, but novelist Samuel Butler was able to express this idea as early as the 19th century, stating that the question of which came first, the egg or the chicken, was likely irrelevant. The chicken is probably just a means by which the egg produces another egg. Professional scientists have their favorites and heroes who serve as examples for them. However, perhaps Charles Darwin's theory of evolution through natural selection has done more than any other scientific work. it has changed the way ordinary people view their place in the world. Charles Darwin was born in 1809 into a famous family. His maternal grandfather was Josiah Wedgwood, who made a fortune in the mass production of fine china. Darwin's paternal grandfather, Erasmus Darwin, a heavy-drinking doctor and poet, wrote a book on evolution in the 1890s. Reason believed that animals change their forms under the direct influence of their environment. This idea was later developed by Jean-Baptiste Lamarck, and it is now more commonly known as Lamarckism. At 16, Charles Darwin was sent to study medicine in Edinburgh. There, he became interested in Lamarckism, as well as the works of geographer Alexander von Humboldt and geologist Charles Lyell, who suggested that Earth is much older than previously thought. In 1831, Darwin paid to board the ship Beagle. On it, he embarked on a journey to the shores of South America. What he observed during the 18 months of his voyage led him to formulate the theory of evolution through natural selection. However, he decided to keep it secret until the late 1850s. In 1858, while working on a book on the subject, Darwin received a letter from his fellow naturalist Alfred Russel Wallace, who was working in Indonesia and had developed a similar theory. This prompted Darwin to publish On the Origin of Species the following year. His work exploded onto the scientific community. Darwin found himself at the center of endless public debates on the topic, and to avoid them, he returned to Down House in Kent. There, he wrote several more books, most of them on the strategies of origin and function of emotions. Charles Darwin passed away in 1882. We all think we know what information is, but this theory reveals its true essence and shows how to format and transmit it as quickly and flawlessly as possible. Today, the theory of information supports a multitude of everyday technologies, from high-definition digital television and DVDs to mobile phones and barcodes on products in supermarkets. The roots of this theory lie in the work of Claude Shannon, a brilliant young American engineer who developed a precise mathematical theory of information in the 1940s. The basic unit of information, by his definition, became the state of true-false, known as a bit, which can take on values of either 1 or 0. Using this mathematical definition, Shannon sought ways to transmit information quickly yet flawlessly, even in the presence of interference. The results of his research form the basis of so-called compression algorithms, which allow entire movies to be recorded on DVDs or transmitted over the internet. This theory also led to the so-called error correction codes, which ensure that phone calls across the Atlantic remain crystal clear, and barcodes in supermarkets are readable even on crumpled peanut packaging. The theory of information can convert the human voice, an image, or a number into codes made up of 2 digits, 1 and 0. These codes are easier to store and transmit. Compared to modern computers, devices from 5 years ago seem like museum exhibits, extraordinarily powerful, with vast memory and hard drive capabilities. Our computers continue to grow, while prices remain unchanged. This incredible pace of improvement was first defined in 1965 by Gordon Moore in an article in Electronics magazine. He predicted that the number of electronic components engineers could fit into each integrated circuit would rise from about 50 to 65,000 in 10 years, roughly doubling every year. In 1975, Moore revised his forecast, presenting this speed in a more modest light, and it is now known by his name, signifying the doubling of computer power every 2 years. Since then, Moore's law has proven surprisingly reliable and is likely to remain so for at least the next decade. This is largely because it set a benchmark that microchip manufacturers strive to achieve. However, in the end, the laws of physics will force this law to yield. There is a limit to how small electronic components can be. Moore himself believes this will happen around 2025. If you are planning to buy a computer, it's better to wait. They are continually getting faster, better, and cheaper. This theory of simplicity deserves all respect, and there are reasons for that. According to the 14th century English logician William of Ockham, elegant explanations are more likely to be true than convoluted and disorderly ones. He advised making fewer assumptions necessary to complete a task, or, as later coined by authors, to shave them in a figurative sense, reducing them to the bare minimum. At the core of this idea is the belief that nature prefers simplicity to complexity. Examples are not hard to find. In the Middle Ages, astronomers, while explaining the motion of planets, tried to complicate their view of the Earth as the center of the solar system. However, simply placing the sun at the center made all that complexity unnecessary. Occam's theory suggested that the heliocentric viewpoint was more accurate, and it indeed turned out to be true. However, finding a simple explanation is often not so easy. For instance, is Einstein's law of gravitation simpler than Newton's? Even today, attempts to turn Occam's razor into an unyielding mathematical rule encounter contradictions. Keep it simple is the essence of Occam's razor. Recognizing this, simplify the theory, leaving nothing but its essential elements. Every time we copy habits, skills, stories, songs, or any information from one person to another, we are dealing with memes. The idea of memes, alongside scientific theories, is itself a meme. The world emerged from theories of universal Darwinism. The idea that whenever any information is copied, it changes and is selected for, suggests that evolution must take place. The most well-known replicator is the gene, but in 1976, Richard Dawkins claimed that culture consists of a second replicator, which he called a meme. People copy memes, including ideas, skills, and behavioral patterns, through imitation and learning. They modify what they copy by making mistakes, intentionally allowing changes, or through creative combinations, and choose which meme to adopt and pass on. The science of memetics studies how memes spread, why some succeed while others fail, and what the implications are for the evolution of culture as a whole. Some memes spread because they are useful or convenient for us. For example, fields of science and medicine, financial institutions, forms of art, and music spread like viruses, even if they are useless. We, humans, are tools of memes, and they use us to survive. All the thoughts in your head compete with one another. They want you to tell someone else about them. They want to get into another head and spread even further. This old problem concerns everyone, from military leaders to card players. Which strategy to choose if we do not know what the opponent is thinking? The solution to such problems is the raison d'être of a branch of applied mathematics called game theory, which, despite its name, deals with something much more serious than a fun pastime. The first understanding of its essence came in the 1920s, when mathematicians invented rules for so-called zero-sum games, where one person's gain equals another's loss. Known as the minimax theorem, This rule advises choosing the strategy that yields the best outcome under the worst circumstances. However, in real life, most games are not zero-sum, and some strategies can lead to both sides winning in some aspects and losing in others. In 1950, American mathematician John Nash managed to develop the minimax theorem to include these non-zero-sum games, greatly expanding the applicability of game theory. For example, evolutionary biologists used it to understand why animals prefer cooperation over fighting each other, while psychologists applied it to study the behavior of criminals in law-abiding societies. Everything, from war to business, is a game, and game theory is a type of mathematics that can help you win. At a party, you are talking to a complete stranger and suddenly discover that you have a mutual friend. You exclaim, "It's a small world." Indeed, it is, and attempts to explain this gave rise to a new scientific discipline known as small world theory, which finds explanations for topics ranging from the spread of diseases to the consequences of globalization. At its core is the idea of a network made up of interconnected elements, from friends and neighbors to computers or multinational companies. Such networks are typically a combination of close ties, like families living in a small village, plus a few random distant connections, such as villagers who travel frequently for work. Mathematicians have shown that a handful of these random connections is enough to shrink vast networks into small worlds, where everyone is connected to everyone else through relatively few intermediaries. Indeed, studies suggest that every person in the world can be connected to another person through approximately 6 intermediaries. In our interconnected world, a seemingly insignificant event can have serious consequences affecting millions of people. You leave home 5 minutes later and miss your train to the airport. Upon arriving at the airport, you miss your flight and learn that the next one will be tomorrow. A 5-minute delay turned into a loss of an entire day. This is a common example of what mathematicians call a nonlinear phenomenon, where minor events do not necessarily have minor consequences. Chaos theory focuses on such situations, where outcomes are often not random and unpredictable. One well-known example is the weather, where nonlinear effects lead to small observational errors that grow over time to the point where all hope of making a reliable forecast is shattered. Forecasters even speak of the butterfly effect, where the flap of a butterfly's wings is enough to cause significant changes to any prediction. Chaos theory provides the tools necessary to distinguish between what appears to be random and, therefore, truly unpredictable phenomena, and those that are rather chaotic. But there is some hope that they were predicted correctly. According to chaos theory, one tiny mistake can lead to a significant event, or even disaster. Every living being is born with certain traits and acquires others throughout life. Acquired traits include deformities, such as scars from smallpox and marks from healed wounds, physical developments, like increased muscle mass from exercise, and skills learned through education, such as the ability to read. From the very beginning, as soon as human thoughts began to be recorded, it was believed that some of these acquired qualities are inherited by the next generation. A common example of this idea was the fact that physically strong blacksmiths often produce robust offspring. This idea can be found in the works of the ancient Greek philosopher Plato. In the 19th century, French biologist Jean-Baptiste Lamarck described the inheritance of acquired traits in his book, which preceded Darwin's theory of evolution. A famous example of Lamarck's theory concerns giraffes. Over generations, giraffes could reach for food in trees by slightly stretching their necks. If the acquired elongated neck of each individual was inherited by its descendants, over time, giraffes would develop long necks. If there is not enough grass, why not try leaves? That is how giraffes developed long necks. This did not happen in the way Lamarck suggested. The ancestors of humans separated from large apes around 6 million years ago. During that period, and up to about 2 million years ago, our ancestors lived in Africa. Then the first humans, called Homo erectus, left Africa and populated Europe and Asia until about 30,000 years ago. Homo erectus and its descendants, known in Europe as Neanderthals, occupied all three of these continents. The question is whether modern humans descended from the type of hominids that lived in Africa and Eurasia, within the framework of an idea called the multi-regional hypothesis, or whether we all descended from a single ancestor in Africa who spread across the globe during a second wave of migration, wiping out local hominids. Fossil evidence has been ambiguous. Then, in the 1980s, genetic evidence emerged. If the multi-regional hypothesis is correct, modern humans' genes should have a common ancestor. Essentially, the degree of differences between our genes is very small. The degree of similarity requires that we have a common ancestor whose age is much less than 2 million years, likely around 100,000 years. During this time, evolution has only slightly altered our DNA. Now, all signs point to modern humans being relatives of a single African progenitor. Genetics proves that all 6.5 billion people living today descended from just a few thousand early Africans. The term sociobiology entered popular consciousness in 1975 after the publication of the book of the same name by Harvard biologist Edward Wilson. Wilson defined sociobiology as the biological study of social behavior. He wrote about an emerging area of biological research that sought answers to many questions. Why are male and female individuals different? What is the function of mating systems? Why are some species monogamous while others are not? And why do animal communities have the structures they do? For instance, chimpanzee groups consist of male relatives and young females who leave home, while in baboons, it is the young males who leave their families. Sociobiology also explores the reasons for phenomena such as companionship, altruism, and territoriality, attempting to answer why some species live in larger groups while others have loners. However, Wilson took a step further. In the last chapter of his substantial book, he offers several biological explanations for human social behavior. This chapter provoked protests from those who felt it touched on their political beliefs. If you think that human society is the pinnacle of sociobiology, think again. Bees, ants, and other insects live in large groups, but for completely different reasons. The inhabitants of a hive are all sisters working for their mother, the queen, aiming to ensure the survival of their newborn sisters so the queen can have as many daughters as possible. Grammar is key to understanding human language. Many animal species possess a developed system of signals that they use for communication, but they lack subordinate clauses, moods, cases, and prepositions that make up the grammar of human language. Human language is infinitely expressive and can be used to discuss and contemplate abstract concepts. Where did language come from? With grammar? The changes required for this lay in the software of our ancestors' brains, which cannot be studied. However, We have two indirect pieces of evidence. The first is the time when human brains began to function like ours. This occurred just over 100,000 years ago, and the brains belonged to people who came from Africa and gave rise to the talkative biped known as Homo sapiens, meaning us. Anatomically, their brains were identical to ours, meaning they possessed the same linguistic capabilities as we do. However, a key change occurred later and affected not just bare anatomy, but how we use our brains. Archaeologists have discovered a wealth of exquisite tools, jewelry, and other artifacts dating back about 30,000 years. Language is what distinguishes humans from animals. Only we can express our thoughts. Now all that remains for us is to come up with something to say. Only humans have brains large enough to encompass all the numerous ways to say the same thing, like a person with a devilish image of themselves on one shoulder and an angelic version on the other. Sigmund Freud's theory of psychoanalysis posits that the human mind is torn. Our mind constantly strives for equilibrium between the needs of the receiving superego and the desires of the insatiable animal subconscious. The central idea of psychoanalysis is that much of this conflict is hidden beneath the cortex of consciousness, surfacing only occasionally in the form of a nervous tic or a Freudian slip. Sex also plays a significant role in this theory. In particular, Freud believed that the source of physical conflict lies in childhood sexual fantasies. The most famous example of this is the Oedipus complex, the idea that children desire their opposite-sex parent and jealously wish for the death of their same-sex parent. What you might say is that you have never had such desires. Your denial would be a perfect example of repression, one of many defense mechanisms that Freud believed we use to tame uncomfortable desires. Such mental maneuvers may temporarily save our reputations, but ultimately they can lead to confusion and make psychoanalysts' clients take ink blot tests. The technique used by the psychoanalyst: patients describe the shapes they see in the ink blots, thereby revealing their repressed emotions. If you see nothing but an ink blot, then perhaps you are truly in trouble. Behaviorism, from the English word behavior, dominated the science of psychology for half a century, even as it ignored all concepts of mind and consciousness and refused to take into account feelings, thoughts, and desires. Instead, it focused on observable behavior patterns that can be measured in a laboratory. Behaviorism emerged in 1913, when psychologist John Watson declared that the degree of a person's learning could be studied just like the famous Pavlov's dogs, which salivated at the sound of a bell associated with food. He argued that the conditioning of an appropriate reflex could be used to turn children into anyone you wished. B.F. Skinner, another American psychologist, invented the concept of operant conditioning, where rats were rewarded for certain behaviors and punished for others. By training them to press levers and run through mazes, he discovered that praise was much more effective than punishment. A key principle for parents and teachers. Skinner founded his own school of radical behaviorism, claiming that all our actions are determined. He also contemplated a utopian society based on conditioning all citizens. Behaviorism explains how people learn from their experiences, both good and bad. Cognitive psychology views people as information processing systems and studies how we think, perceive, learn, and remember words. Cognitive comes from the Latin word to think, and the term cognitive psychology was introduced by UN Lyric and Sear in 1967. This was an intriguing shift from the dominant behaviorism, which limited all research to mental processes. The new cognitive psychology studied internal mental events and evolved into a rapidly developing science of artificial intelligence. In this new science, the mind was likened to software, and the brain to the hardware of a biological computer. Human actions, decisions, and thoughts were forms of information processing and depended on data received from the senses. For example, the study of the brain's visual system showed how incoming information through the eyes is processed in layers of retinal cells, the midbrain, the sensory area of the cerebral cortex, and sent to brain areas capable of recognizing objects or controlling actions and speech. What is it? A brain or a computer? Cognitive psychologists argue that there is almost no difference, and the brain is a mechanism for processing information. Genes control most fundamental life functions. When they go awry, we may develop diseases, from Alzheimer's to cancer, and we can pass inherited diseases to our children. Genetics in medicine seeks to find better, if not perfect, treatment methods by investigating the genes responsible for the ailment. This sounds quite simple. Find the faulty genes responsible for the disease, remove them, and insert fresh copies. For some time, this is how genetics in medicine was envisioned, but reality turned out to be more complex. While some hereditary diseases result from a single faulty gene, most diseases arise from complex interactions among a multitude of genes. Restoring even one gene has proven to be an incredibly challenging task, and to date, no one has been cured of a genetic disease. Genetics has been more successful in creating drugs that regulate gene-related diseases. For example, the drug Herceptin was developed by identifying genes involved in certain forms of breast cancer. But even such drugs have very limited efficacy and are yet another example of how genetics in medicine has not lived up to the hopes associated with it. Perhaps one day, gene therapy will become a panacea. But first, geneticists need to understand precisely how the DNA strand builds the human body. Once we learn this, we will be able to notice when it goes awry and fix it. Proponents of alternative medicine, from acupuncture to yoga, view it as therapy that can be applied alongside traditional medicine. For its opponents, it is a heap of unproven tricks that ensnare patients while the main burden falls on traditional medicine. There is some truth to this. Some conditions that seem to respond well to complementary therapy, such as pain and depression, are linked to a powerful placebo effect, where patients believe they feel better after what is essentially useless treatment. Scientific experiments that tested such treatments yielded conflicting results, not least because many trials lacked sufficient funding. However, it cannot be denied that some forms of complementary medicine, particularly acupuncture and meditation, are effective for conditions like headaches and stress, and there is certainly no doubt about the popularity of alternative medicine. Such treatments have long been widely used in Asian countries. In Japan, 75% of the population regularly resorts to them. Their popularity is now growing in the West. Alternative medicine is becoming increasingly popular, although in many cases its efficacy has yet to be proven through large-scale controlled clinical trials. Herbal medicines are one form of alternative medicine. Many patients trust them implicitly, while most doctors criticize them. Once, doctors chose treatments for their patients based on personal beliefs, information they had received many years ago in medical institutions, or advice from their tennis partners. Sometimes this approach worked, sometimes it did not. Evidence-based medicine seeks to place such decisions on a more scientific foundation based on the results of carefully controlled clinical trials. Now, doctors can access databases online that contain the latest information on the most effective treatment methods based on reviews of clinical trials conducted by internationally recognized experts. But do they actually do this? That is another question. Many doctors still prefer to act independently. Either they are too busy to read reports, or they are skeptical about the reliability of clinical trials, or they do not want to limit themselves and thoughtlessly apply so-called proven treatment methods. However, proponents of evidence-based medicine insist that doctors must always combine strong evidence with their judgments about the needs of the patient. Every doctor has favorite medications and treatment methods, but where is the evidence that you are receiving the best treatment? Imagine being given a pill and told that it will relieve your headache and improve your condition, even though the pill contains nothing but chalk. This is the placebo effect. From the Latin, I shall please, in medicine, this term is used to describe treatments that have no real medical effect and work on the power of suggestion. First described in the 1920s, the placebo effect is now an integral part of evidence-based medicine. In clinical trials, drugs are compared to placebos. This can be a pill that looks exactly like real medication, but contains no active ingredients, or acupuncture needles that look convincing and feel just as convincing, but do not actually penetrate the skin. In a randomized controlled trial, half the patients receive the real drug, while the other half receive the placebo. If both groups show the same improvements, the conclusion is clear. The new drug is useless. The placebo effect is incredibly powerful, and its effectiveness even increases if the patient receives a larger pill, a pink one instead of a white one, or if it is prescribed by a highly respected doctor. A pill does not necessarily have to contain medication. Thanks to the placebo effect, you may feel better, even though you now know that the effect may not be as strong.